Hello students, I am Dr. Manju Gupta. Today I am going to explain the chemical reactions of aromatic amines. This is the second part of the reactions of amines. The most common reactions of aromatic amines are electrophilic substitution reactions. In electrophilic substitution reactions, in aniline or in any aromatic amine, the lone pair of electron which is present on the nitrogen, this NH2 group or this lone, because of this lone pair of electron, it acts as activating group or ortho-para-directing group and increase the electron density on both the ortho positions and para position. Here you can see in the resonating structures of aniline, as the electron pair of nitrogen transfers towards the benzene ring, first the negative charge formed on the ortho position, then it shifted on the para position, then again on the ortho position. That means in both the ortho position and para position, the electrophile can attack. The NH2 group in aniline or in aromatic amine, it acts as a very strong activating group. Since it is a very strong activating group, it always substitutes all the three hydrogens. That means hydrogens present on both the ortho position and the para position, substitutes all the three hydrogens by the electrophile. So, to avoid the formation of polysubstituted compound and to control the reaction or to deactivate the effect of amino group, first it is necessary to protect the amino group or to decrease its activity. To decrease the activity of NH2 group, we convert it into anilide group by the acetylation reaction. This acetylation can be possible by reacting with acid chloride or acid anhydride. When amines react with acid chloride or acid anhydride, here I am taking acid anhydride. This molecule is acid anhydride. This molecule is acid anhydride. So it is converted into acetanilide. This molecule is acetanilide. It is converted into acetanilide, and this acetanilide has anilide group which is less activating. It also creates electron density or increases the electron density on both the ortho and para position, but it is less reactive or active as compared to the aniline group. So first reaction is the nitration reaction. First electrophilic substitution reaction of aromatic amine is nitration reaction. You know that nitrating mixture is the mixture of concentrated nitric acid and sulfuric acid. In case of direct nitration with a mixture of concentrated nitric and sulfuric acid, that means when we carried out the reaction of any amine with reaction of any amine, suppose I am taking NH2, aniline. Reaction of aniline with concentrated sulfuric acid and concentrated nitric acid. Reaction with concentrated sulfuric acid and concentrated nitric acid. In this condition, nitronium ion is formed as the electrophile and the products formed in this particular reaction. Suppose if this is NH2, nitro group can be present on the meta position. Nitro group can be present on the para position, and ortho isomer can also be formed. But the amount of the formed product, the meta substituted meta-nitroaniline is formed as 47% meta-nitroaniline. Para-nitroaniline is formed as 51%. This is para compound, and 2% formation of ortho compound. Now, there is one question. When NH2 group is ortho-para-directed, then how is it possible the formation of meta-nitroaniline? And in this particular reaction, appreciable amount of meta-nitroaniline is formed. That means direct nitration of aniline is not suitable for the formation of para and ortho compound. What is the reason for the formation of meta-nitroaniline? Since the reaction is carried out in a strongly acidic medium, this is H+. Since the reaction is carried out in acid medium, the lone pair electron of nitrogen present in the amine group, it can form a bond with H+ of acid and convert it into anilinium ion. Now, since the lone pair of electrons on nitrogen are no longer available for the activation of the ring, it acts as the deactivating group and direct the incoming nitronium ion towards the meta position. This is the reason why meta-nitroaniline is formed, because aniline is converted into anilinium ion, and anilinium ion is not a ortho-para-directing group, but anilinium group is the, or NH3 plus group is meta-directing. So nitration is carried out. If we want to prevent the formation of meta-nitroaniline, so first we have to protect the nitro group. First we have to protect the nitro group. For the protection of nitro group, first we carried out the reaction of nitrobenzene aniline with acetyl chloride, CH3COCl. Then in the presence of pyridine, there is the elimination of one molecule of HCl and formation of acetanilide, NHCOCH3. Acetanilide. When this acetanilide is subjected to nitration, that means reaction with concentrated HNO3 and H2SO4. This group is only ortho-para-directive influence and produce ortho and para-nitroacetanilide. And HCOCH3, at ortho position there is nitro group, and HCOCH3 at para position there is nitro group. This is ortho nitro acetanilide, and this is para nitro acetanilide. Now nitro group is now the nitro group is present on the ortho and para position. Now the second step is to again the group which we have protected by converting it into anilide group, we convert it back into amino group by the hydrolysis reaction. By acidic hydrolysis reaction, always ortho compound is formed as the minor product, because of steric hindrance, and para product is formed as the major product because of symmetry. This is hydrolyzed into orthonitroaniline, and this hydrolyzed into para-nitroaniline. So in this way, we can prepare ortho and para-nitroaniline. Second reaction is halogenation. Here we are taking example of for halogenation reaction is bromination. Again, you can see in this example, NH2 is a strongly activating group. It produces negative charge on both the ortho and para positions. When the reaction is carried out with bromine water, in this case, when we are taking aniline and the reaction of bromine water, here we are taking bromine water, then all the three positions are substituted by bromine and there is the formation of 2,4,6 tribromoaniline. That means polysubstituted product is formed. Now, if we want to prepare monosubstituted product, for this, first we have to convert the NH2 group into analyte group by reacting it with acetyl chloride. When we react with acetyl chloride in the presence of pyridine, removal of HCl and formation of NHCOCH3. After this, when we add bromine in acetic acid, there is the formation of para-bromoacetanilide. This compound is converted into 4-bromoacetanilide. Since the analyte group is big enough, so ortho positions remains sterically hindered and bromine cannot attack on the ortho position. Once the 4-bromoacetanilide is formed, we can subject it to hydrolysis in acidic medium and it will convert it into para-bromoaniline, 4-bromoaniline. So if we want to prepare monosubstituted bromo compound or 4-bromoaniline, first it is necessary to protect the NH2 group. Then after hydrolysis, it becomes converted into or hydrolyzed into NH2. If we want to prepare both ortho and para-bromoaniline, in this condition, the reaction of aniline is carried out with bromine in carbon disulfide solution. In the presence of carbon disulfide solvent, this will decrease the activity of NH2 and form two different products, para-bromoaniline and ortho-bromoaniline. This is ortho-bromoaniline and this is para-bromoaniline. So two different compounds or two different isomers we can obtain by reacting aniline with bromine in disulfide carbon disulfide solution. Third reaction is sulfonation reaction. This reaction is unusual. Why it is unusual? Because it takes place under drastic condition, that means in the presence of strong acid and at high temperature. For example, reaction of aniline. Reaction of aniline with H2SO4. When aniline react with H2SO4, it forms anilinium hydrogen sulfate. Actually, in this particular reaction, H2SO4, concentrated H2SO4 is not acting as the oxidizing agent, but it acts as a strong acid. So since aniline NH2 has a basic character and H2SO4 is a base, so by the reaction of acid and base, there is the formation of a complex NH3 plus HSO4 minus. This is known as anilinium hydrogen sulfate. Anilinium hydrogen sulfate. When this anilinium hydrogen sulfate is heated at 453 Kelvin temperature, this complex undergoes rearrangement and form sulfonilic acid, NH2 and SO3H. There is the removal of one water molecule and form sulfonilic acid. This is sulfonilic acid. Forms sulfonilic acid, and this sulfonilic acid exists in the form of dipolar ion, which is known as Zwitter ion, NH3 plus and SO3 minus. It exists as a Zwitter ion. So this is a third electrophilic substitution reaction, sulfonation. Next is the mercuration. In a mercuration reaction, when amine is heated with mercuric acetate, when amine is heated with mercuric acetate, any aromatic amine, suppose NH2, aniline, when aniline is heated with alcoholic solution of mercuric acetate, CH3COO whole twice Hg. Alcoholic solution of mercuric acetate. It forms orthoaminophenyl NH2 Hg OCOCH3 plus CH3COOH. This is orthoaminophenyl mercuric acetate. So this was the mercuration reaction. After that, last reaction is coupling reaction. Coupling reaction is initiated by the diazotization. Always coupling reaction is carried out after diazotization. You know, diazotization is the reaction of aromatic amine with nitrous acid or with sodium dilute solution of sodium nitrite in the presence of concentrated HCl. At lower temperature, there is a formation of benzene diazonium chloride. This step is diazotization, in which diazonium salt is formed. When this diazonium salt reacts with any electron-rich substance or phenol or naphthol or aniline, it forms a colored compound by coupling reaction. For example, here you can see the reaction of diazonium chloride with phenol. It couples and form benzene, a yellow colored dye, which is known as solvent yellow. This is the coupling reaction. So all the five are electrophilic substitution reactions of aromatic amines. Thank you.